Good afternoon, everyone. My name is Sai Aditya Pradeep, and I'm the Scientific Program Manager for AIM. And today we'll be doing the AIM Ideas Summer Research Program. The focus today is on our second webinar, which is a hands-on tutorial. Uh, it's the first of our tutorial series. So our third webinar will be a second tutorial. And in this series, we'll be focusing on approximating functions with neural networks. Huge shout out to Haizo for helping us with this, as well as Nick for organizing this. This is part of AIM and Ideas programs, which I'll talk a little bit about before handing it over to Haizo. So the mission of AIM EFRC is to build an AI-enabled inverse design approach for fundamentally understanding and integrating material manufacturing design that's specifically targeted for advanced thermoplastic polymer composites. The IDEA's NSF NRT traineeship focuses on training the next generation of STEM students to develop expertise across multiple disciplines, specializing in AI-enabled inverse design, uh, advanced composites, and manufacturing. This particular series that we are organizing explores the transformative role of neural networks in science and engineering, with a focus on their growing potential to revolutionize data analysis and computational modeling. Our second webinar will feature more of a hands-on demonstration showing how neural networks can approximate simple mathematical functions, along with an introductory Python programming tutorial designed to guide students through practical implementation. A bit of an acknowledgement to both of these programs. So this series is brought to you by the Artificial Intelligent Manufacturing Paradigm, or AIM for Composites, which is an energy frontier research center funded by the Department of Energy, the Basic Energy Sciences Office under this particular award number, and by the National Science Foundation Research Traineeship Inverse Design Training in Advanced and Sustainable Composites under this particular award number. We have these webinar series at quite a bit of a recurring basis. So please feel free to follow us on social media, whether it's for AMEFRC or Ideas NRT, and you'll be posted on, you'll essentially come to know when our next webinar series is going to get aired. So with that, I will hand it off to Haizo. Again, thank you, Haizo and Nick. Yeah, please take it away. Yeah.
Right. So welcome everyone to the first hands-on tutorial. So our focus today is on how to approximate simple function with fundamental forward neural network, or to say FNN. And in the next webinar, we're going to dive deeper to learn how to use PNN. So a bit of a callback from the first webinar, we have learned that NN is nothing but a universal approximator, and they can theoretically approximate any scientific or engineering process if we figure out the suitable input and output. So there is always a surrogate model based on NN, which can map the input to the output. Previously in the introduction, we have talked about that the approximation process of NN is essentially like a optimization, where the weights and the biases are gradually approximated to the optimal values. So we are going to find out the basic principle that allows those weights and biases to reach their optimal values. In that way, we would have a deeper understanding of NM approximation. After that, we're going to learn how to use Python to approximate a simple function, and what are the most important factors or the parameters we should pay attention to when we tuning our NM approximation. So we previously talked about the conventional ways that we have learned in the math textbook to approximate a simple function like f of x is to use a series approximation like a polynomial series or Fourier series. The basic idea is to just adjust the right terms or right coefficients of the base subfunctions to approximate the target or f of x that we want. But the issue is those series are just not powerful enough to approximate any complex function that we want, or sometimes we just lack the math experience and don't know which is a suitable series that we can use. So we need something universal to help us to do the job. So last time we also introduced the fundamental structure of a simple FNN, which is based on a bunch of neurons each has adjustable weights and biases that we need to approximate. In one neuron, our inputs on the right side like goes through the linear summation that incorporates new weights and biases, then goes through an activation function to get the final output from this neuron. If you look at the overall NN structure, all the inputs goes through the series of neurons and finally put together to like form up an output, which is our can be like consider our approximation result, or to say our prediction result given by the NN. So here we just use a very simple FMN with only one hidden layer with 3 neurons as a very simple example. The process that like the input X goes through the NN to the output Y can be like mathematically expressed in the equation like this. The form is kind of like very similar to the traditional polynomial form or Fourier series form that we showed before, where the weights and biases are the coefficients that we need to approximate. The activation functions are very essential in the NN. They are always in nonlinear form. Therefore, they add nonlinearity to the NN. So the nonlinearity is a very unique feature that the NN has. If you think about it, if we don't assign activation function to the NN, what would the NN equation look like? So it would look like this in the like simple example of our 3 neuron FNN. If you just simplify it, it makes no difference to a common linear regression. So when the NN involves more hidden layers or neurons, the NN provides no unique approximation, but a polynomial approximation if there are no activation function at all. So that's why the activation function is very important, and the different like specific tasks may require different activation functions. So knowing the fundamental structure of the NN, we need to know how those adjustable weights and biases are automatically found their optimal values. So the goal of the optimization is to make the prediction Y gradually approaches the real Y. The gap measured by the loss function, therefore, the goal of the automation is to make the loss minimal. So if we consider one specific iteration during the approximation process where we assume X and Y data are fixed, therefore they can be seen just like constants in the loss function. So the only independent variables we have in the equation will be the weights and biases. So our mission is to design a like approximation algorithm which locates the optimal weights and biases to make the loss function minimal. If we just focus on one specific weight like W, so the loss is sole function of this W. So in simple function graph, it may look like a curve like this. Our like initial W is not optimal. It may like located randomly at any point, like point A or point B, and our mission is to let the point go to the location where the loss is minimal. It is like climbing down a mountain, and we need to let the point know the exact direction of going downward. If you are the point and you are standing in some location and you're trying to going downward, so what information could give you the right direction? So you would probably say the slope where you are standing. So in math language, it will be the first derivative of the loss function as a location, or to say the gradient if there are like multiple weights. So the idea is we move a step towards the direction that the gradient gave us. In this way, we can march to our destination to the optimal location. But there may be a problem if we just directly use the value of a gradient as our like actual marching step. So just like in this simple example, you say the derivative is around like 20 at the point A. If we just take step to the left at the size of 20, we will just go outside of the function map. That means the direction is right, but the step size is kind of too large. So we can actually add a scaling factor to scale down the step. So this factor is called learning rate. And with super learning rate, we can just like the points gradually matching to the optimal locations. And this concept, this concept and this whole process is called gradient descent. So the selection of a suitable learning rate is also very important. If we just use a learning rate which is too small, it would take a long time to reach like our optimal location. So the convergence will be very slow. And if we use a learning rate that is too large, it will cause a divergence. You can say on the rise subplot, the point is just constantly bounding between the two sides without reaching the optimal location. So this is called a divergence during the process. So we'll still use this some example of a 3-neuron FNN, and we define the loss function using MSE, which is a mean square error. We would have the loss function of this specific 3-neuron FNN looks like this. So if we just focus on the optimization of one way to say W11 in one iteration, so we can say all other variables as constants through the channel gradient for W11 is calculated. So gradually goes through the gradient descent process, we would finally have the optimal value of W11 that gives minimum loss. So all weights and biases are going through the same process, and it's like climbing down a multi-dimensional mountains to reach the mountain valley. And the whole process that optimize the weights and biases with gradient reference given by the channel is called backpropagation. Here I would recommend all of you guys to watch the videos made by Cerebro and Brown. That really makes a very good visualization to help you understand some of the important but sometimes very abstract concepts in deep learning. So we also need to know the concept of the training and the testing. So the training is about using the data to optimize the weights and biases, or to say to inform the NN to approximate. So we use loss to measure the quantity of the NN because the mission of the training is to minimize the loss function. And in contrast, the testing is that when the training is over, you have a well-trained NN, you just inject the data which is inside of a training data set to say whether NN gives a good prediction. So we use prediction error or prediction accuracy to measure the quantity of a trained NN. In theory, if we have a lower loss, and we would definitely have a lower prediction error. So two things are sort of a positive related to each other. So in our specific case to approximate function today, the general task can be like divided into two kinds. So the first kind is to approximate the knowing reference function with NN. We take some training samples from the real reference curve to like form a training data set and train this NN with these samples. Then compare the train NN curve with the reference to give a testing accuracy. And the second kind is to phase the curve with just samples. The first things we need to do is divide all of the samples into training data set and testing data set. And we use training data set to train the NN and use the test data set to verify whether our like prediction is right or not. So to summarize a little bit, so the content that we just learned is just those following ideas. So the basic ideas of the approximation by the NN is kind of similar to the polynomial or Fourier series. The weights and biases are just the things that we need to optimize. The activation function adds the nonlinearity into the NN, which makes NN a universal approximator. Each weights and biases is gradually optimized through gradient descent, just like the climbing down a mountain, and the global optimization is called the propagation. During the approximation, the learning rate is also very important. You decide the convergence or disconvergence. And a classic approximation has both training and then testing parts. So after learning, like understanding all of this, so it is time to get your hands on the actual code. So we are using Google Colab online platform to make sure that everyone is able to run the codes without having any hardware or environmental trouble. But I would highly recommend you guys to run the code on your own laptop or desktop if you can, because Colab sometimes just gives limited hardware resource for free users, and sometimes the running environment is temporary. Basically, whenever you're trying to restart the code, you need to reset the running environment every time. So sometimes it will really tricky. So from the questionnaire from last webinar, basically nearly everyone has the experience using Python. So I presume everyone knows the simple operation like plus, minus, multiply, square, and defining a simple function. So it is completely okay if you don't, because the demo code is very simple and easy to get hands on. So first we create a empty cloud notebook with a IPY .IPYNB in your Colab, and upload the Python code that need should have already shared with you to the content folder. And there are 3 files ending with .py and one ending with .IPYNB. Then copy the main code of the demo to the notebook you just created. And you can just first use the preset parameters and click the run button, and there should be something coming out. When you finish the training, there should be a result graph as output, and the total training time and the Colab will vary from 5 minutes to 10 minutes. And those are the instructions to run approximation. So let's just look at the codes. So the first 2 lines is to import necessary Python packages. I presume most of you know what the NumPy is. So this package is one of the most common mass libraries for Python programming. So the run.py is written by myself, and it packs all the necessary approximation inside, and it pulls the nn.py and the dataprep.py to use their functionality. So nn.py is for creating an NN model with given layers, and the dataprep.py is for creating training and testing data sets. And the random function of the NumPy fixes the randomization, so it basically ensures the duplicability of the certain approximation that we conduct. And the diff here is to define the function that we want to approximate. So here's a simple example we use here is a function of x times sine of pi x. Then we will pull the subfunction of round.py to initiate the NN setup. We assign the approximation function that is the one we just defined, and we set up the x range between -5 to +5. So and the total number of training points that we sample from the function is 61. And then we define NN consisting of 3 layers, and each one layer consists of 32 neurons. So, and we set up a learning rate to 5 times 10 to the power of -3, and we just gonna let the training run for 10,000 iterations and put out every 1,000 iterations. So as we know, some of the parameters are very important to notice. So the first one over here is the sample number. Basically, you need to good samples that can actually reflect the complete feature of the function. You can see here we just change the number of the sample, even though the accuracy doesn't vary very much. The first one just fails in approximation in some of the local positions, because those positions are not sufficiently represented by the enough samples. And the second one is the complexity of the NN. And so a universal conclusion is that more complex NN surely bring you higher potential to get a better result, but it just would bring the non-proportional cost as well. So you can see that if we use 5 hidden layers of 64 neurons in each layers compared to the middle one, it doesn't increase it does increase a bit of accuracy, but the training time is almost doubled. And the suitable learning rate is also very important. So as we addressed for many times, a small small learning rate, of course, can avoid divergence, but sometimes a too small learning rate might slow down your training process. You can say that there's only 1% increase in accuracy, but the training time is almost double as well. So those are basically those are the most important things for beginners to know. So here I would just give a very quick simple demo of the instructions, so everyone can just try later, try the code on the Colab by yourself. So if you have any question, please free to ask. So basically, we just log into our Colab and we just create a new notebook over here. And there's a man code window over here. So we can click this folder button and we upload the files. Nick should have a send you to the guys. Let me see. So there's 3 Python files and 1 notebook files. So we upload to this content folders, and we'll basically just copy the first line to the 18th line to our online notebook, and we just hit the run button. So here we just use the default function that I use here. So you can just change this function to any function that you want to approximate. And you can try to change the learning rate, the complexity of the NN, and the sample number to see the difference between those results. So this execution time should be for this function specifically should be 7 minutes to 8 minutes. So you would like to try with this code. So if anyone of you have a question, you can just free to ask.
Hi all. So if you have any questions, please use the Q&A feature in the webinar. Nick can read out the questions, or Haizo can see the questions there as well.
Yep.
If you would prefer to ask the questions more with a audio or a video, let us know, and then Nick can ensure that you can share it with share your questions verbally as well.
So basically, when you run through 1 or 2 minutes, there should be some output from every 1,000 iteration coming out. And you can see this training loss and test error, they are just gradually going down. So when you have a test error less than 1%, that means your training is pretty good. Nick, can you see the chat box? So students are asking to get the recording of this tutorial. How can we see the MS in the output? So this is a SME over here. So because I use SME as a loss function over here. So basically, you can define any loss function as you like. So, but the MSE is the most fundamental one, and everyone just use it.
So the LR is the observed data.
LR is the learning rate. So I don't know. You remember just what I said. So learning rate is something that scale down the derivative. So in every iteration, there's like for every weight and biases, there's like just like I said, they are like climbing down mountains. So the iteration just like a step. But sometimes this like margin step will be too large. So we set up a learning rate to sort of like scale down this large step to make sure our points that can be like gradually approached to the optimal location.
Okay. Thank you. I think one more question also.
I think this question is kind of like general. So it's very depends on what kind of a test that are you doing. So for our topic, today's topics, so to approximate the simple function, like you can just set a constant learning rates, just the and I think the prediction won't be very bad. But if you have very complicated tasks like the actual engineering process, you may consider like a different stage of training. Like in stage one, you set a learning rate is kind of it's kind of large to make sure your the stage one learning is very fast, and you in stage two you just gradually set a like smaller learning rate to make sure the training process goes slower and don't like bouncing between the valleys. So these are like kind of a general idea to tuning NN. So it really depends on the specific problem, and for most of the time we just you just do a training and see the outcome, and according to the outcome, and you just try strategy, and you say the new strategy have a better outcome.
Did you answer this question, Haizo? How do we ensure
Yeah,
we are not overfitting the solution? Okay, you did. Okay.
yeah.
All right.
I think one reason of overfitting is because your testing samples and the training sample is not reflecting the same features, because your NN is trying to approximate the training data set, but the testing data sets sometimes not being considered. So you need to make sure your two data sets are like equally sampled, and sometimes just sometimes training like too much will cause this some like phenomenon. Just you need to sort of like observe your like train loss and test error. Sometimes you say your train loss is going down, but your test error is going up. That means you may have an overfitting.
Okay. There's one question in the
That's all right.
Q&A panel.
Of course. So there certainly will be sort of the algorithm that using like dynamic learning rate during the training, and in fact, people dealing with very complex models, they just using dynamic learning rate. Like one of the strategies to like adjust the value of learning rate with the value of the derivative. You say when you go down, if the slope is too large, you want the learning rate just smaller. You want the step is smaller. So this definitely is some approximation that use like a dynamic learning rate.
And then there's one question here. In your presentation, you showed different activation functions like tan H. Does it depend on input-output relationship? Which type of function to use?
So for this case, we just use like tan H function over here. for different like texts, for like image recognitions, people are like more likely to use a ReLU or Sigmoid. So it also depends on the specific task that you are dealing with.
One more question. Are there any rules of thumb for picking those activation functions?
Sorry
Are there any rules of thumb
ru-
for picking these activation questions? Like, do you have any ballpark starting point or something like that, or some good guesses
uh
to pick those activation functions?
so basically you can just try different activation functions. You start with a tongue age and like firstly you just set the iteration steps a little bit slower, set the epochs in a small number, like to say you try like 10,000 as a first, and set up the same parameters but choosing a different activation function to say which one is better. So for scientific problem, like people dealing with like PINN, like DNO, they are all using a tanh function. So I think this one, so for if you like study a like physical based problem or like scientific problems, you will probably like likely use this one. So people doing like image recognition, they're more likely to use the ReLU function.
Great. Thank you. Any questions from the SCSU students? We have Trey. Megan, Jalil. Okay. If not, Nick, do you mind sharing the questionnaire with all the panel with all the participants? Anything else, Haizo, from your side? Sorry, before we move on to that. Yeah.
Well, I think that's all for today. So next webinar, we're gonna learn how to use PIN to solve the differential equations. There's one like ODE example and PD example.
Okay. Nice. So a request to all the participants, please answer it's a very short questionnaire that Nick has just shared with everyone. If you don't mind, please do answer. We would like to get some feedback. We're constantly improving these hands-on webinar series. So any feedback from you guys will help us tweak it in the next version. So yeah. And I think we are having webinar 3 in the next couple of weeks. Is that right, Nick?
Yes, it is the 24th.
24th. Okay.
So about 2 weeks from now.
Okay.
Yeah.
All right. So please do take the time and fill the questionnaire.
Yeah, next time we'll do PINs, but our PIN is like just based on DeepXD. So we're gonna use the package of the DeepXD to implement the PIN.
Yes, Eric, I think next time we'll do PNNs. That's what Haizo was mentioning. Yeah. Okay. Good. Nick, has everyone answered the questionnaire?
You got
Or
every
most people
slowly
have?
but surely, but like so we got
Okay.
18 out of 21. So
That's pretty good.
yep.
Okay.
So
All right. Haizo, do you want to add anything else? I think this was good,
Well,
like
I
good
think that's
Q&A
all.
session. Okay.
Yeah,
All right.
that's all I want to talk about today.
Okay. All right. Great. Then if that's the case, thank you all the participants for joining us, and thank you for filling questionnaire as well as asking questions. I think it was a good Q&A session with Haizo. All right, great. Then we'll see you in 2 weeks for webinar 2. Thank you, everyone.